Cool. All right, let's get started. Kia ora, everyone. So here is lesson number 2 of your week 7 lockdown work. Our whangia today is processing how to balance the complex redox equations. So just as a reference point, you guys did the simple ones in week, was it last week? Yeah, it must have been last week. You guys did the simple ones last week, and that was just basically looking at stuff that I gave you both half equations, and you were looking at the electron numbers and trying to match those electron numbers up so they cancel out and things like that. Now what I want to do is actually show you guys the process of how to balance the complex redox equations. We will see some simple ones again, but the main thing about these equations is that you just need to follow the sequence of events and you should be okay. With the assessment, the good news is that you don't need to do any of these equations for the achieved. So if your goal is to pass, if you never master this, then you'll be okay. But if you do want to merit or excellence, you do need to be able to balance these equations. So do keep that in mind. All right, so on our checklist today, lots of things are coming off because we are practicing various components. The first one is balancing those half equations. We need to be able to do the half equations first. Then we're going to be combining those equations together to form a full equation. Again, you guys have kind of started to see this already with the electrons and having to match those number of electrons. And then we're also tying in that use of vocabulary. And again, you guys have seen this before, so it's not going to be anything too new. All right, so there are multiple steps that we are going to be looking at for the balancing of the redox equation. I'll put them all up on the board, but I will have them in the examples that I do. So I will refer back to this, so don't worry about copying it down or reading through that. I'm just showing you guys overall, this is the sequence of steps that you need to do. So I'll give you guys 2 examples to get you guys going. The main reason why I'm giving you guys 2 different examples is because I know that the follow-up work that I've assigned gives a large variety of questions in different formats. And so I just want to get you guys kind of used to seeing them. The other reason I want to show you both of them is that way I can start explaining to you guys what you're going to be looking for, what you're going to get on the assessment, and how to also use the resource sheet. So in this first example here, we've given you the full equation, but this full equation is not balanced. And that's what we need to do in today's lesson. To help kind of visualize what's going on, I've put in a video that I'll play. And basically, it's the mixture of those 2 things. Now, there's potassium permanganate, which is the purple color. You're adding iron to sulfate, which is a pale kind of green. And what you should observe happening when you mix those 2 things together is that the solution goes colorless. This only occurs if the permanganate is acidified. If it's not acidified, it will instead turn brown. But that's what we're looking at in that first reaction. And I just want you guys, like I said, to start seeing observations and tying those observations to species that are involved. The iron 3 is actually a pale orange color, which is kind of leaving that kind of undertone there. But the main thing is that it's basically pretty colorless. Now, in case you're wondering where I got those colors from, I'm getting them from the resource sheet. So if we look at this resource sheet here, here's my iron 2 aqueous, meaning dissolved in solution, green. Iron 3 aqueous, orange. I should update that and write the word pale, because pale is probably a better way to describe it, because it's not like super intense color-wise when you compare it to other things. Down here is the permanganate, and it is purple, and it's going to the manganese ion, which is colorless. You might have also noticed in that video that they had other things in there, such as the sulfate and the potassium, but we're not looking at them in this equation. So this equation, all I've done is I've given you the active components. I've removed any spectators. In the next example, I'll show you how I know which ones are spectators and which ones aren't. But let's first go through the process of figuring out how to balance those half equations. So let me just move that out a little bit so we can see a little bit better. I'm going to move this over so that way we can start writing. All right. So Here are the steps on the left that we're going to be doing. I'll try to hopefully have enough colors so that way I can actually match the colors to the step. I might need to do some things where what happens when I do that? Oh, cool. Yeah, I can get all the colors. Awesome. All right, so first step that we need to do, just like we've been doing previously, is we need to go through and figure out which is the oxidation half and which is the reduction half, because I'm going to be pulling these guys apart and doing half equations first before I put them together. So I'm going to be using either the oxidation numbers and or observations to help me figure out what's going on. In this example here, I only need to worry about the oxidation numbers, but in the second example, I'll show you how I can use the observations to help me. So basically, I want to split these reactions into the oxidation and the reduction, and I can then use that to identify oxidant and reductant. So let's go through and just label everyone's oxidation numbers as I'm working. So iron 2, it is an ion. It's monoatomic, so its oxidation number is the same as its charge. I see that there's iron 3 over here, so I'm annotating it down here. I see that manganese is also its own ion by itself, so that I'm giving a positive 2. And the last thing that I have is my permanganate, and we're going to have to do some oxidation math when I look at that. So that guy over there, oxygen is -2, and I have 4 of them, so -8, and it's supposed to equal -1. So when I do the math, the manganese and the permanganate is going to be +7. I hope you guys can see where I've kind of got that from. And that's where I'm getting that 7 from. So this guy's +7. Oxygen's only appearing on one side of the equation right now. For a very specific reason. It's not actually involved in the redox reaction, but I can put its oxidation number down too, just so I can see it. All right, so let's start labeling things. I see that the iron 2 going to iron 3, this guy over here, my oxidation number has gone from +2 to +3, so it's gone up by 1. So since my oxidation number is increasing, that is my oxidation reaction, making the iron 2 my reductant. Really important that we're using our vocabulary words. All right, second thing that I'm looking at, maybe, I'm just trying to think if I can grab a different color, maybe a different red. So we're still in that first step. All right, what I'm looking at here is my oxidation number for manganese is going from a +7 to +2. So that is a decrease by 5. So this tells me that the oxidation number has gone down. So that is my reduction reaction. Oh, let me get that spelled correctly for you guys. Making my permanganate the oxidant. So that's my first step, and that's my first step done. I figured out what reaction's what, and then I've done my labeling. All right, step number 2 then is I need to write down the main species involved in the half reactions and their products, and then make sure that's balanced. So I'm going to basically do all the steps first for one half of the equation, and I'll do all the steps for the other half of the equation, and then we're going to put them together. So first step is let's do the iron, because the iron is going to be a lot easier for us to see and understand. So I have iron 2 going towards iron 3. I like to leave space in case I'm going to be writing any electrons down and things like that. And I always want to double check to make sure, I have space for everybody. So when I'm looking at this, the oxidation number has increased. That means electrons have been lost. And I look here and I've gone from a +2 to a +3, so I've lost 1 electron. And we know with oxidation that I should have the electrons on the product side because they are being lost. And again, I'm going to try to give myself space when I'm writing because I want to make sure that in case I need to do any multiplications or put any coefficients in front, I have space for that. Cool, so that's my step done. Then they want me to balance any oxygen atoms by adding water. Not a problem, so I skip that step. Next step, they want you to balance any hydrogens that you've either need or that is the result of adding the water. Again, didn't add water, so don't need to do it. Oh, I skipped too far ahead. I was too eager. Anyway, step number 5 is to balance the charge by adding electrons. Let me get a lighter blue because that's what I was using. So basically what I'm looking at, charge on this side is +2. Charge on this side is +3. And so basically I'm looking at the charge of the ion, I'm looking at how many of those ions that are there, and I'm figuring out, what is basically what I'm working with. So since this is +2 and that's +3, I'm going to need to have those numbers match. So I'm going to be adding an electron to this side of the equation because by adding that electron there, I now bring this overall charge to +2, and now they match, which is good. It means that I do have my half equation done. Hopefully that makes sense. So yeah, that's sorted. That's the half equation. So I'll tick that off, and then we're going to hold off on 6 and 7 because I need the other equation for that. All right, so going back to the drawing board, I'm going to go back to my pink color because that's representing the first step in my process, and I am thinking about the permanganate, MnO4 minus, going towards the Mn2 plus. I'm leaving space on this side, and I'm leaving a space there, so that way I have areas to keep writing. So that's my first step. I check to see if it's balanced. So I have 1 manatees on this side, 1 on the other side. That's all good. So I've done my second step. Then, here are the new things that we are looking at. So I need to balance the number of oxygens by adding water. So when I look over here, I see that I have 4 oxygens. So what I need to then do onto this side of the equation is I need to add 4 waters. You can only add the oxygen as water. So those 4 here become my 4 in the H2O that I see. That is very messy. So that's where that's coming from. So I've done that step, tick that off. Next thing I need to do is then balance for the number of hydrogens. So either I might have hydrogens present in that equation I need to balance for, or I need to balance the hydrogens that I have just added over there. Now, keep in mind there is a subscript behind that's 2, and there's also that superscript in front. So remember, you have basically 2 hydrogens already times the 4. So both of those are going to be applying. 2 times 4. We have a total of 8 hydrogens. When we add it to the other side, we are going to be adding them as hydrogen ions. So 8H plus ions. And that then balances for the hydrogens that will be in the water on the other side. So basically these hydrogens and those oxygens will combine together to form the water molecule. So that step's done. Step number 5 is to balance my electrons, and we're going right back to those charging. So when I look at this side, I have a +8 because each one of those hydrogen ions provides a +1, and there's 8 of them. And I have 1 permanganate that's providing a -1. So total charge on this side is +7. Now let's look at this side over here because I want them to match. So I see that this is +2 from the manganese ion, and there's nothing that the water is contributing. Water is a neutral compound, so it doesn't have any charge to it. So my total on this side is +2. So those are the 2 numbers that I'm looking at, and we want the charges to match. Remember that I'm talking about charges and not oxidation numbers, and I should actually write these so that way the charges are actually behind. So that way we know we're talking about charge. Did I do it on that one too? I did. I think I was so used to writing oxidation numbers. Okay. Cool. So when it comes to getting those charges to match, you can only add electrons. You are not allowed to add anything else. So basically, I take a look at the higher of the two numbers and I need to bring it down. Now, in order for me to bring it down, I need to add 5 electrons because that's going to then equal that positive 2 that I'm trying to get. So add 5 electrons to that side. Now my charges match. So this is one of my half equations, and this is my other half equation. So in order to get merit, you need to get these half equations. I feel like for merit off the top of my head that you need to get 1 out of the 2 half equations correct. Getting the full equation and putting them together is what you need to do for excellence, and it's not that much of an extra step. So last thing then is we need to combine these equations together, and you guys have already seen how to do this. We're going to be looking at our electron numbers. Actually, let me backtrack before I do that. Something you should notice, hopefully, when you're looking at these oxidation numbers is that we see how the oxidation number has gone from +7 to +2 in this one here, and it's gone down by 5. This number here should match the number of electrons you've added. Same thing for the other one. This has gone up by 1, so you should be losing 1 electron. So just keep that in mind that your electron number should be matching what you're referring to in changes of oxidation numbers. So yeah. Anyway, let's put these guys together. So looking at these electron numbers, I need these electron numbers to match, and I'm looking for the lowest common denominator of the two of them. In this case, it is 5 because this guy has 5 and this guy has only 1, so I can easily multiply this whole equation by 5 and I can put them together. So that would be 5, that would be 5, and that would be 5. When I then put these two equations together, my electrons should be on opposite sides and they cancel. So this one here is on the product side and this one here is on the reactant side. So those two 5s do match and they do cancel out. And now I can just copy down this information and put it as my full equation. So let's just do that. Let's do that purple. All right. It's also easy maybe if you can layer your two half equations on top of each other, so that way you can easily kind of put them together, line them up so that way your half equations, the arrows are matching, so that way it's very easy to tell what's on the reactant and product side. The only reason why I've spread it out so much is because I'm doing extra annotations just to talk about the instructions. Anyway, so looking at the order, I had 5 Fe2 plus. That's all of the reactants on this side, so let's go to this half of the equation. The electrons have already canceled out, so I'm not writing them in my final overall balanced equation. Next thing I have listed is, whoopsie, now I'm opening up Excel, is the 8 hydrogens, and then I have my permanganate listed as my other component. It doesn't matter what order you guys write the chemicals in, they just need to be on the right side of the equation. So that's that half done. If you want, you can tick it off as you're going to make sure you haven't forgotten anybody. On the product side, I have the 5 Fe3 plus, and then I still see I have the manatee's ion, and then I have my 4 waters. So everybody's accounted for. That's my full equation there, and that's what you're going to need if you want an excellence. Cool. If you want to double check your work, you can check the charges on there to make sure the charges cancel out. So this here is 10 plus 8 minus 1. So total charge on this would be 18, 17. This side over here, I have 5 times 3, it's 15. Stop doing that. Plus 2. Just a good way if you want to double check. Plus, in this case, 0. since water is a molecule, has no charge. 15 plus 2, 17. So the charges match. Just a good way to double check to make sure your equations are correct. But that's what you're looking at. So that's my first example. That one's a pretty straightforward one because we've given you the products. In the second example that I've given you, let me zoom out a bit. I have not given you the products. So I've given you acidified potassium dichromate, and I've mixed it with sodium sulfite. I've given you information about the color change, and you need to use the resource sheet to identify what ions are involved, so that way you know which expectators to ignore, and then also determine what the products are. So this one requires a few more steps. You are still using oxidation numbers to figure out who's who, but you're going to need to use the observations as well because you don't know what you want to grab. So breaking it down, the acidified potassium dichromate gives me potassium ions and the dichromate ions. So I'm just writing that down there. So I have to be using one of these two. And then the other thing I have is the sodium sulfite. So sodium is the Na, and then sulfite is SO3 2-. So that's the other pair. You're only selecting one of the two ions in that ionic compound. Otherwise, it would auto redox itself. So I basically need to figure out, of the two, which one am I using? And the way you figure it out is two things. First, you look at the resource sheet to see what's there, and you look at the color change to see if that helps you. So when I look at that resource sheet and I go through it, the first thing I will notice when I go through is that there's no sodium and there's no potassium being listed. So that's a pretty good hint that you're not using them. The other thing to do is look for the color change. So I'm thinking about stuff that's orange, and it says it's going from orange to green. Well, if I look, I see dichromate here is an orange color, and I see the chromium ion being a green color. So that hints to me what the reaction is. It doesn't say it's going from orange to metallic luster, so I know I'm not going from the dichromate to the chromium element as a metal. So really use those observations to help you out. Now, yes, there's other things on there that are orange and green, but in the context of the question, they haven't given you that reagent, so don't use them. The other thing I'm looking for then is my sulfate, which is right here, and figuring out what it goes to. I know it's colorless, and there's lots of other things around there that are using the sulfate that I can also see it's colorless. I can rule out one of them already. I know I'm not using the sulfur dioxide because that's a gas and there was no notion about bubbles being formed. So use your logic when you're going through this, but I can rule out so far that that is not being used and that is not being used. I also can figure out based off of the observations that this dichromate is probably going to the chromium ion because that matches the color changes that I saw, because that one is orange and that one is green. So that helps me kind of verify what's going on. So now let's, again, look at the resource sheet because I don't know what the sulfite is becoming yet. Remember that you are given these redox pairs and they're given the reactants and the products. Remember how I said it's going to be given in the orientation that this direction is the reduction direction. So basically, to hint of how you're trying to grab things, you should grab something from this side of the table. And since I've grabbed the dichromate from this side of the table, whatever I'm grabbing for the other component needs to be going in the opposite direction and being oxidized comes from this side of the table. You'll notice that sulfate is only over here, SO3 2-. So it has to go from sulfite to sulfite to sulfate. So that's the direction for that pair. It can't be going in this direction because this is not what you're starting with, and also you cannot have two reduction reactions going forward. So that's how I figured out that sulfate is my product in that example. So like I said, first one, dichromate, I find it's going this way. It matches the color observations. The problem with the sulfite and the sulfate is they're both colorless, so I can't use that to help me. But I know I need to pick something from this side of the table, and I can see that my sulfate, sulfite is here, going this direction to my sulfate. That's how I figured it out. So hopefully that makes sense. Just do lots of practice. Anyway, this guy here is going to SO4 2 minus. The next thing to kind of keep in mind is double checking which is oxidation and which one's reduction. So I said that this one is the reduction reaction and this one's the oxidation reaction based off of what I was grabbing off the resource sheet and knowing that the ones that are going forward are reduction, the ones going backwards are oxidation. But let's just double check with the oxidation numbers. Cool. So I might actually grab this different color red to help us. So some things to remember when I'm looking at this. Oxygen is -2. I have 7 of them. It is equal to -2. So that's -14 equals -2. So there's 12. And I have 2 chromiums. So divide by 2, divide by 2. That's how I get the chromium. In this case is +6. And this one's going to be +3 because I know that's my... the charge is going to match the oxidation number. This verifies that it is a reduction reaction because I see that the oxidation number is decreasing by 3. I've gone from +6 to +3. So it verifies what I said earlier. Keep in mind that you are only referring to oxidation numbers as one atom. There is a total of 12, but for each chromium it is 6. All right, let's double check my sulfurs. I already ruled out oxygen very quickly because in both examples, oxygen is in a polyatomic ion. It's going to be -2 on both sides, so that's not going to influence it. So let's look at sulfur. Oxygen is -2 times 3, that's -6, equal to -2. So in this case, sulfur is going to be +4. In this case, I have 2 more oxygens, so -2 times 4 is -8, set to -2. So in this case, sulfur would equal +6. Again, this confirms that I do have an oxidation reaction because I see my oxidation number has increased by 2. We have gone from a +4 to a +6. So that does match what I was talking about earlier. And I do have an oxidation and reduction reaction. So first step completed, figured out which one's which. This is oxidation, that's reduction. That makes dichromate my oxidant. And it makes the sulfite my reductant. Let's make sure we're using our vocab. Cool. All right, let's do our half equations. This time around, I'll try to stack them on top of each other so that way it's easier to cancel. Let's start with the dichromate one. That one's... Yeah, let's do the dichromate one first. All right, cool. So I'm going to put my arrows right in the middle to make it nice and easy. Dichromate is Cr2O72-, and then it's becoming Cr3+. So my first step is to write down the reactant and the product, and this is something that you now haven't seen before, balancing that active component, which is the chromium. So I see there's 2 on this side. So since there's 2 on that side, I need to make sure I have 2 on the opposite side. So I'm putting a 2 in front to represent that. Let me just erase that. There you go. All right, done that step. Next one is balance the number of oxygens by adding water. So I see that there are 7 oxygens here, so I'm adding 7 waters. That's where that number is going. Just to show you, I'm just going to erase that. All right, done that step. Tick it off. Next step is to balance the hydrogens. So looking at that, that's 2, and there's 7. So 7 times 2, I have 14 hydrogens there. So I'm adding 14 hydrogens, and that will balance that out. Cool, done. I'm just erasing things so you guys can see things a little better as I'm processing them. All right, last step then is I need to add electrons by checking those charges. So that's +14. Let me just do that. 14. plus, in this case, -2. So total on this side is I have 12. In this case, I have 3 times 2, so that's 6. Nothing on this side because that is water and that has no charge, so that just equals 6. So I have 6 and I have 12 on the other side. Remember, we can only add electrons, and I'm taking that bigger number down. So in this case, I'm going to be adding 6 electrons because by adding the 6 electrons, I'm now bringing this number down to 6, and these guys match. So that's my first half equation. All right, let's now do the second equation. Again, in this case, I'm lining up my equations so you guys can see what I mean by lining them up and then making it easy to cancel out. So I have the sulfite becoming the sulfate. I check to see if my sulfurs are balanced, and they are, so I don't need to do any work there. My next step is to add water. So I see on this side that that's 3 and that's 4. So I only need to add 1 water because that 1 water will then total up 1, 2, 3, 4. So both the oxygens on both sides add up. So that's how you're going to deal with it in that situation. All right, now that I've added water onto this side, I need to add the hydrogens. So I see that there's 2. So I'm adding 2 hydrogen ions there to balance it. We can't create or destroy matter. And now I'm on to my last step, looking at those electrons. So let me just tick it off. We've done that. We've done that step. We've done that step. We've done that step once. Now let's do it again. All right. So that's 0. That's -2. So it's -2 on that side. That is -2. And that is +2 because you have a +1, you have 2 of them. So total, I have 0 on this side and I have -2 on this side. So in order to balance it up, I need to add electrons to this side because I want to bring that number down to -2. So I'm adding 2 electrons. And that will bring that number down to -2. So take whatever is the more positive number and bring it down. All right, on to our final step. We look at the the electron numbers, and we're mindful that we want them to cancel out. So this case it's 2, this case it's 6. Common multiple they would share is 6. So I'm multiplying this whole equation by 3. So by multiplying it by 3, I now can get enough electrons for that to balance out. So if I'm going through and multiplying everything by 3, it'd be 3 H2O, 3 sulfites, 3 sulfates. That 2 now becomes a 6 because it's 3 times 2, and that 2 becomes a 6 because, again, 3 times 2. So that is my new half equation that I have. All right, now let's put these bad boys together. Oh, I don't like how that is there. There we go. All right, so first thing I like to do, draw my arrow, so that way I know reactants and products. I can cross out the electrons because the electrons are now balanced, 6 and 6, and now it's just a matter of writing everything else down. Keep in mind that there's water and hydrogen on both sides of those equations, so you're going to need to cancel them out too. So what I'll do first is I'll write down the non-hydrogen and water bits. So I see that there's dichromate, so I'm writing Cr2O7 2-, and I'm writing down the sulfite. And now I need to write down the water and or the hydrogen, depending on how things cancel out. So when I look at this side, there's 14 hydrogen ions. When I look at this side, there's only 6. So I can take away all 6 of those. I subtract 6 from the 14, and I would get 8. So plus 8 hydrogen ions is what you should have on that side. I'm going to move these all a little bit closer because that was really far away. So that's all of everything on that reactant side. All right, next bit, like I said, I'm going to go through and write everything else down first. So there's my CR3. Just going through and double checking everybody. It's really useful to use tick marks. All right, sulfate. And then once again, we're looking at the waters at this point because we've taken care of the hydrogens. So I see there's 3 waters on this side and there's 4 waters on this side. So all these 3 waters will go away, and 7, and I'm subtracting away 3. That brings that to 4. So 4H2O. And that's my final equation. Again, if you guys want to double check, you can check with the charges. Let's see, that's -2, -2, +8. So that's 4, -6. Sorry, +6. That is -6, and then that's nothing, so that I did something wrong. Hold on. 3 times 2. Why is my math not working? Oh, I forgot to multiply something over here. That's right. Cool. All right, 3, -6. So that's -8 plus +8. That equals 0. And then that, yeah, +6, -6, 0. So both of those charges match. The other thing you can do if you want to double and triple check your things is just count various atoms just to make sure. The main one to double check would be the hydrogens and the oxygens. So in this case, I see that there's 8 hydrogens. I see 2 times 4, that's 8 again, so that's okay. The telltale is going to be those oxygens. So I have 7 here, 3 times 3 is 9, so I have a total of 16 oxygens on that side. 3 times 4 is 12, plus another 4 oxygens on that side, that's 16 as well. So it's just a good way to double check it to make sure you haven't accidentally created or destroyed matter. You don't need to do it, but if you find yourself having extra time on the assessment, it's worthwhile to do it because it just kind of idiot checks yourself because you don't want to make a silly mistake. There's going to be because if you make a mistake on that full equation, you're not going to be able to get excellence. And unfortunately, with the no resubmission policy for merit or excellence, if you do make a mistake on these equations, we can't allow you to correct them. So like I said, just double and triple check. The merit is being able to get one of these half equations. The excellence is getting both half equations and then the final equation too. But hopefully by having those 2 different examples, you then know what to do and look for. So yeah, this, like I said, is an example of one where we haven't given you the products, but we have given you observations to help you kind of understand it. And just to verify, to make sure that those observations are right, here is a nice little video so you can see what I was talking about. Here's your potassium dichromate, starts with an orange. The reducing agent, they're just named general, but sodium sulfite works as it. And you can see it's going to a really pretty green color. So, like I said, observations time. And we'll do this when we're back in the lab. All right, Kapai, really good work for finishing the 2nd lesson of this lockdown. So just to summarize, today you guys should be balancing those complex half equations. Follow-up work is not lesson number 7. It is lesson number 4. Let me fix that. Make sure you're putting that evidence into that week 7 lockdown work. There's also CPR quiz for you guys to practice that. Remember, both of these are on the Google Classroom assignment. Hopefully that makes sense. The main thing about this is just lots and lots of practice. And next week, I'll show you guys how to put it all together for the assessment.